Imagine for a moment that the global economy is not a collection of banks, governments, corporations, and consumers. Imagine instead that it is a gigantic engine. Every transaction is a moving part. Every investment is a rotating gear. Every currency is a lubricant that keeps the machine operating. Now ask yourself a deceptively simple question. What happens to every engine that runs continuously? It gets hotter. Not necessarily in temperature, but in complexity, in instability, in friction, in noise. Perhaps the greatest misconception about modern finance is that its biggest challenge is creating more money. In reality, its greatest challenge is managing the ever-growing disorder that naturally emerges whenever billions of people exchange value under imperfect information. Every new loan, every speculative bet, every policy intervention, every unexpected crisis introduces another layer of uncertainty into the system. Economists describe this through incentives, market cycles, and behavioral psychology. Physicists would recognize something surprisingly familiar: entropy. Entropy is often misunderstood as chaos itself. More precisely, it measures the number of possible configurations a system can occupy. A system with low entropy has relatively few possible arrangements. A system with high entropy can exist in countless different states, making prediction increasingly difficult. This idea extends far beyond physics. Information theory adopted entropy decades ago to measure uncertainty within communication. Computer science relies on it to understand randomness. Cryptography depends upon it to produce secure keys. Even biological evolution constantly balances order against entropy by consuming energy to sustain living structures. The economy, although fundamentally different from a physical system, exhibits remarkably similar patterns. It continuously generates uncertainty. Prices fluctuate because information arrives unevenly, expectations diverge, confidence rises and falls, incentives shift, new technologies emerge, political decisions alter capital flows overnight. Every participant acts with incomplete knowledge, creating a constantly evolving landscape of possibilities. That landscape is economic entropy. This does not imply that markets are broken. Quite the opposite. Dynamic markets require uncertainty to function. Without uncertainty, there would be no discovery process, no entrepreneurial risk, no innovation, no opportunity. The problem arises when uncertainty compounds faster than trust can adapt. Consider money itself. Money performs several essential functions. It acts as a medium of exchange, a store of value, and perhaps most importantly, a unit of account. The last function is often overlooked. Money is society's measuring stick. It tells us how much one thing is worth relative to another. But imagine trying to build a bridge using a ruler whose length changes every morning. Measurements become unreliable. Engineering becomes difficult. Planning becomes nearly impossible. Now imagine conducting an entire civilization using a measuring stick whose purchasing power changes according to political priorities, emergency interventions, debt expansion, or shifting monetary policy. This does not automatically invalidate fiat currencies. They have enabled enormous economic growth and remarkable financial flexibility. Yet flexibility comes with a price. Every discretionary adjustment introduces additional variables into the system. Interest rates move, balance sheets expand, liquidity conditions change, expectations react, asset prices adjust. New expectations emerge from those adjustments, creating feedback loops that often become impossible to fully predict. The result is not immediate collapse. It is a gradual increase in informational complexity. One policy influences another. One intervention requires another intervention. One distortion creates another correction. Like heat accumulating inside an engine, these layers of uncertainty build over time. History repeatedly demonstrates this pattern. During periods of relative stability, confidence encourages greater leverage. Greater leverage amplifies risk. Amplified risk eventually demands intervention. Intervention reshapes incentives. Those altered incentives plant the seeds for the next cycle. None of this requires malicious intent. It is simply what complex adaptive systems tend to do. The fascinating question is whether a monetary system can be designed differently. Not by eliminating uncertainty entirely. That would be impossible, but by minimizing the number of variables that participants must constantly reinterpret. This is where Bitcoin introduces something fundamentally unusual. Bitcoin does not promise stable prices. It does not promise economic growth. It does not eliminate speculation. Instead, It removes an extraordinary number of monetary uncertainties from the system itself. Its issuance schedule is known decades in advance. Its maximum supply is fixed. Its validation rules are public. Its consensus mechanism is transparent. No committee wakes up on a Tuesday morning to decide that 22 million coins might be preferable to 21 million. No emergency meeting adjusts the monetary base because financial markets had a difficult week. No central authority modifies the protocol according to election cycles or political priorities. This predictability is often described as monetary discipline. Another way to understand it is through the reduction of informational entropy. Notice what Bitcoin actually fixes. It does not fix human behavior. People remain emotional. Markets remain volatile. Fear and greed continue to exist exactly as before. Instead, Bitcoin fixes the rules governing the monetary foundation itself. Imagine playing chess where the rules change every 10 moves. The strategy becomes secondary because players must constantly adapt to a shifting framework. Now imagine playing chess where the rules never change. Players may still make mistakes. Some players remain stronger than others. Surprises still occur. Yet everyone shares absolute certainty regarding the underlying system. Bitcoin attempts something similar. It reduces uncertainty about the protocol so that uncertainty can exist primarily within human decision-making rather than within the monetary rules themselves. This distinction may appear subtle, but mathematically it is profound. Information theory teaches us that predictable systems require less information to describe. When future behavior follows deterministic rules, participants devote fewer resources to interpreting the system itself. Those resources can instead focus on evaluating businesses, technologies, productivity, innovation, and genuine economic activity. In other words, complexity shifts away from the monetary layer toward the productive layer. That transition matters because every civilization ultimately depends upon reliable coordination. Millions of strangers cooperate every day without knowing each other personally. Farmers produce food for people they will never meet. Engineers design bridges for cities they have never visited. Software developers write code used across continents. None of this coordination would be possible without shared systems of trust. Traditionally, institutions provide that trust. Bitcoin attempts something radically different. It attempts to embed trust directly into mathematics. Not because mathematics possesses moral authority, but because mathematical rules are indifferent to human preference. 2 plus 2 equals 4, regardless of politics. SHA-256 produces deterministic outputs regardless of ideology. Digital signatures verify ownership regardless of nationality. Consensus follows computation rather than reputation. This leads us toward one of Bitcoin's most misunderstood components, proof of work. Many people assume miners are simply creating coins by solving meaningless mathematical puzzles. That interpretation misses the deeper purpose entirely. The hash calculations themselves have almost no intrinsic value. The importance lies in what they prove. They prove that measurable physical resources were irreversibly consumed. Electricity cannot be unspent. Time cannot be reversed. Hardware experiences real wear. Opportunity costs become permanent. Proof of work therefore creates something extraordinarily rare in the digital world: objectively verifiable cost. In most digital environments, copying is essentially free. A photograph can be duplicated infinitely. A document can be replicated instantly. Software scales at nearly zero marginal cost. This abundance is one of the Internet's greatest strengths. But abundance creates a problem for digital scarcity. If creating an asset costs almost nothing, creating another identical asset also costs almost nothing. Scarcity disappears. Bitcoin approaches this challenge from the opposite direction. Instead of making digital information difficult to copy, it makes legitimate monetary creation expensive to achieve. Not expensive because someone charges a fee. Expensive because the laws of physics require energy expenditure. This is a profound distinction. The protocol does not ask participants to trust miners. It asks them to verify evidence that miners paid an unavoidable physical cost. Energy becomes security. Security becomes credibility. Credibility becomes trust. Trust becomes monetary value. None of these transformations occur through magic. They emerge because every participant can independently verify each step without requiring permission from anyone else. For perhaps the first time in history, a global monetary network links digital certainty to measurable physical expenditure through transparent mathematical rules. Whether one believes Bitcoin will ultimately succeed is a separate question entirely. The deeper observation is conceptual. Every durable structure in nature, from living organisms to ecosystems to civilizations, must continuously consume energy to maintain order against the natural tendency toward increasing disorder. Perhaps monetary systems are no different. Perhaps lasting monetary order cannot emerge from promises alone. Perhaps it requires an irreversible expenditure that anchors digital trust to physical reality. And if every system that resists entropy must ultimately pay an energetic price, then the next question becomes impossible to ignore. Could Bitcoin's greatest innovation be neither its scarcity nor its decentralization, but the mathematical architecture through which it continually transforms energy into monetary order? If every enduring system must spend energy to resist disorder, then Bitcoin presents us with an extraordinary possibility. Perhaps its most important function is not creating digital money at all. Perhaps its deeper role is continuously removing economic heat from the monetary system by forcing the creation of trust to obey the same fundamental constraint that governs order throughout nature. To understand this idea, imagine the engine of a high-performance race car. As long as fuel burns inside the cylinders, power is produced. But power is never free. Alongside useful work comes waste heat. The harder the engine operates, the more heat accumulates. Without an effective cooling system, the engine eventually destroys itself, not because the engine was poorly designed, but because concentrated energy inevitably produces instability. Modern economies exhibit a surprisingly similar characteristic. Economic activity creates tremendous wealth, innovation, and prosperity. Yet every expansion also generates side effects. Credit expands faster than income. Asset prices rise faster than productivity. Leverage multiplies gains while quietly magnifying hidden risks. Speculation attracts more speculation. Optimism feeds additional optimism until confidence itself becomes one of the largest assets in the system. This growing instability is not merely emotional. It becomes embedded within prices. When capital becomes increasingly inexpensive to create, financial decisions gradually separate from the physical reality of production. Debt can grow faster than output. Financial claims can multiply faster than the goods and services they ultimately represent. Expectations begin to reinforce themselves. Like heat trapped inside an engine, these positive feedback loops accumulate invisible stress. History repeatedly demonstrates what happens next. Eventually, the system reaches a point where accumulated instability must be released. Sometimes it appears as inflation, sometimes as debt crises, sometimes as banking failures, sometimes as collapsing asset bubbles. The exact mechanism differs, but the underlying pattern remains remarkably familiar. The system attempts to restore balance. The release is painful precisely because the imbalance had been building for years. Now compare this with Bitcoin's design philosophy. Bitcoin refuses to accelerate monetary creation simply because demand increases. It does not issue additional supply during euphoric markets. It does not expand in response to political pressure. It does not reward optimism with easier monetary conditions. Instead, every new coin enters circulation through exactly the same process. Real-world energy must be consumed. Real-world hardware must operate. Real-world opportunity costs must be paid. Nothing about public enthusiasm changes this equation. This is where the analogy of a digital thermodynamic cooling system begins to reveal its value. Again, this is not a literal physical cooling process. Bitcoin does not lower Earth's temperature or violate thermodynamic laws. Rather, it provides a conceptual framework for understanding how the network continually absorbs economic pressure by translating speculative demand into measurable physical cost, instead of allowing that pressure to alter the monetary rules themselves. Imagine demand for Bitcoin suddenly doubles. In many monetary systems, increased demand for money might encourage expansion of supply. Under Bitcoin, something entirely different occurs. The protocol remains unchanged. The issuance schedule remains unchanged. The consensus rules remain unchanged. Instead, competition among miners increases. Hash rate rises. Energy expenditure rises. Mining difficulty eventually adjusts. The system absorbs additional economic pressure without modifying its monetary foundation. Notice where the adjustment occurs, not inside the rules, inside the cost of securing the rules. This distinction is mathematically elegant. One variable remains effectively constant while another adapts automatically. In engineering, systems often become more stable when critical constraints remain fixed while adaptive variables respond to changing conditions. Bitcoin follows a remarkably similar architecture. Supply is constrained, consensus is constrained, issuance is constrained. Competition adapts, energy adapts, hardware investment adapts, market prices adapt. The protocol itself remains astonishingly indifferent. This indifference is one of Bitcoin's greatest strengths. Nature itself does not negotiate with human preference. Gravity does not become weaker because lifting heavy objects is inconvenient. Conservation of energy is not suspended during economic recessions. Likewise, Bitcoin's monetary rules remain unaffected by popularity, fear, politics, or urgency. Some researchers have pointed toward another fascinating concept that enriches this discussion: Landauer's principle. Landauer demonstrated that erasing information carries an unavoidable minimum energetic cost. Information processing is not completely detached from physics. At its deepest level, computation has physical consequences. Bitcoin does not directly implement Landauer's principle in any explicit engineering sense. However, it reflects a compatible philosophical insight. Digital systems are not independent of the physical universe. Every validated transaction ultimately depends upon hardware. Every block depends upon electricity. Every cryptographic calculation occurs inside physical devices consuming measurable energy. Bitcoin therefore refuses to pretend that purely digital trust can exist without any physical foundation. Instead, it continually reconnects cyberspace with the real world. That connection may prove more important than many people realize. For decades, the internet became increasingly efficient at eliminating physical costs. Communication became nearly free. Publishing became nearly free. Distribution became nearly free. Replication became nearly free. These transformations unlocked extraordinary innovation, yet they also revealed a difficult challenge. If everything digital can be reproduced almost infinitely at negligible cost, how can scarcity genuinely exist online? Many attempts relied on trusted intermediaries, others depended upon legal enforcement. Still others required centralized databases. Bitcoin proposed something radically different. Scarcity should emerge from irreversible expenditure rather than institutional permission. The distinction is subtle but profound. Permission depends upon authority. Expenditure depends upon reality. One can revoke permission. One cannot recover electricity already consumed. One can rewrite regulations. One cannot reverse the passage of time embedded within accumulated proof of work. This observation leads us toward the phrase that inspired this discussion: mathematical inevitability. The word inevitability deserves careful treatment. It does not mean Bitcoin is guaranteed to become the world's dominant money. Markets never provide such guarantees. Technologies fail. Societies make unexpected choices. Superior ideas sometimes lose to inferior competitors for reasons unrelated to mathematics. The inevitability lies elsewhere. Suppose humanity wishes to create a decentralized digital asset possessing several specific properties. It cannot rely upon trust in any individual. It cannot permit arbitrary monetary expansion. It must resist counterfeiting. It must remain globally verifiable. It must allow strangers to reach consensus without central coordination. Game theory immediately imposes severe constraints. Cryptography imposes additional constraints. Economics introduces further constraints. Physics contributes another layer. As each constraint is added, the number of workable designs shrinks dramatically. Eventually, one principle repeatedly reappears. Someone, somewhere must bear an irreversible cost that cannot be forged. Otherwise, creating consensus becomes cheaper than attacking consensus. Otherwise, creating value becomes indistinguishable from copying information. Otherwise, scarcity dissolves into abundance. This is not merely a technological observation. It is a mathematical one. The cost of producing secure consensus cannot asymptotically approach zero while simultaneously preserving objective scarcity in a permissionless environment. Whether future systems use proof of work, new cryptographic breakthroughs, or architectures not yet invented, they will almost certainly encounter the same fundamental requirement. Trust without trusted intermediaries requires unavoidable constraints. Bitcoin's answer is energy. Future systems may discover alternative answers. But no system escapes the mathematics entirely. Every robust design must anchor itself to something that cannot be fabricated at zero cost. Seen from this perspective, Bitcoin resembles a cooling mechanism because it continuously channels abstract human demand into concrete physical expenditure rather than allowing monetary rules themselves to absorb that pressure. It does not eliminate speculation. It does not eliminate bubbles. It does not eliminate irrational behavior. People remain beautifully and frustratingly human. Instead, Bitcoin ensures that the foundation beneath those behaviors remains remarkably stable. Perhaps this is why the network has survived crises that many believed would destroy it. Exchange failures came and went, governments changed, mining migrated across continents, market prices collapsed and recovered repeatedly. Public narratives shifted from enthusiasm to ridicule and back again. Yet block after block, approximately every 10 minutes, the protocol continued performing exactly the same task. No excitement accelerated it. No panic slowed it. No ideology persuaded it. The rules remained astonishingly consistent. That consistency may ultimately become Bitcoin's greatest contribution. Not because consistency guarantees success, but because civilizations depend upon reliable reference points. Maps are useful because they remain stable while travelers move. Clocks are useful because they measure time consistently regardless of our emotions. Mathematics is useful because equations do not vote. Bitcoin aspires to become another such reference point, not by eliminating uncertainty from the economy, but by removing uncertainty from the monetary rules themselves. Perhaps that is the deeper meaning hidden beneath all the discussions about price, mining, volatility, and adoption. Perhaps Bitcoin is not fundamentally a machine for creating wealth. Perhaps it is a machine for transforming energy into verifiable trust, trust into durable monetary order, and durable order into a foundation upon which increasingly complex economic cooperation can emerge. Whether history ultimately confirms this vision remains unknown. But the architecture itself offers a remarkable lesson. Throughout nature, lasting order never appears without cost. Stars burn fuel to produce light. Living organisms consume energy to maintain life. Civilizations expend resources to preserve institutions. And Bitcoin, through an elegant combination of mathematics, cryptography, game theory, and physics, proposes that digital monetary order should obey that same timeless principle. Not because nature requires Bitcoin, but because if digital civilization is ever to build money that stands independently of human discretion, it may discover that the price of lasting order has always been the same. Energy transformed into trust through rules that mathematics refuses to negotiate.